physics students. A couple of people asked me about light part 3, which is basically what we call total internal reflection. Okay, so I'm going to go over the slides that I think are pertinent. There's 59 slides. I wish I could print them out, but I'm not going to do that. So I have my camera focused right now on the slides, and I'll move them over as I do the problems. So for instance, the do now, it says a light ray traveling in air enters a second medium and it slows to 1.71 meters per second. What is the absolute index of refraction of the second medium? Well, that's a pretty good question. I like that question. Again, if you guys can print out a reference table, that's the best, but I try to include them on every one of these lessons. And there we go. Index of refraction, which in light is n. C is the speed of light. And v is the velocity of the light we're looking at. So nothing's ever going to be... The only thing where they're both the same is when the top and bottom numbers are c, speed of light in a vacuum, and it's going through the vacuum of, say, space. Then it's traveling at the speed of light. Now, any other medium it travels through, it's going to slow down. Essentially, the speed of light in air is the same as the speed of light in vacuum, which is not 100% true, but kind of true. Okay? So, for all intents and purposes, we say that the index of refraction for air is 1. Okay, so let's just look at something else, because I guess it doesn't slow it down that dramatically. I guess it's people's figuring. So I have this n equals c over v. N equals c over v. They told me the velocity of the light that I'm measuring is 1.71 times 10 to the 8. The speed of light, again, I have to go to my reference table. The speed of light in a vacuum is 3 times 10 to the 8, of course, meters per second. Well, this 10 to 8 meters per second crosses out. So my n is really 3 divided by 1.7. Well, 3 divided by 1.7. Let's look at, I'm just going to use my phone. Don't use your phone, Flans. Okay. 3 divided by 1.7. 1.76 looks like roughly. I'm going to turn my light on there. I'll show you. 1.76 roughly. So I'm going to say it's 1.76. I'm going to go over here just out of curiosity. Which one's close? Is there one here that's close to 1.76? Nah. There's nothing in our indices of refraction that they give us that's close to 1.76. So I can't even really tell you what it's passing through. It must be something that's rather hard for light to pass through. Slows it down quite a bit. 1.76. I mean, that's... I'm looking here. The only two things on this list that are greater than 1.76 are zircon and a diamond. So, very, very interesting. So, things that really have high indexes of refraction. The only thing that isn't bigger than is the top 2. So, it's in the top 3 of those lists. But, we don't know what it is, so don't worry about it. They don't ask us what it is. And now if I look over here, one of my problems here is 1.75. It must be C. Because I didn't put 1.71. That's why it came out to 1. Okay. No big deal. Okay, so it had to be C. All right. Good. All right, so let's move on. Let's look down this thing here. Okay. Our objective, I'll let you guys determine if you want. Here we have total internal reflection. So as you see here, a laser is being shot out of over here. It is going and it's hitting here. Now instead of the laser continuing out to the faster medium, being air or a vacuum, it reflects off that surface and stays within. This is a big concept they used in, fiber optics. Fiber optic signals here are based on the idea of total internal reflection, that you can keep the data within a secured space. It's not going to go out. It can keep bouncing around, traveling at the speed of light, which is fast, and it stays within. So total internal reflection does have a lot of benefits. Okay, more total internal reflection. There was a video. Okay, so we know something here real quick. Angle of refraction and angle of reflection, right? So it's always the same. So if light is hitting a mirror, let's say, at 39 degrees, it's also reflecting off the mirror at 39 degrees. That's why the only way you see yourself directly in the mirror is if you look straight into the mirror. Okay, so keep moving. This is a good question. It says, skipping a rock across water has one thing in common with skipping light off a media boundary. So if you ever skip a rock off of water, back down to the Flans demonstration here, okay? So let's say you're standing on the shore, and you got the water here, and you want to skip a rock, okay? So you're standing on here. Now, if you throw it like this way, it's going to go into the water and sink to the bottom, right? You don't want an extreme angle. What you do want is a very slight angle. If you ever see people do this or try to do it, or you tried to do it, you want a very slight angle. You want this to hit the water almost going like this. So people, you'll see they get down, they kind of throw it almost underhand or sidearm, very low to the ground, and it hits like that and skips off. And that's how you get it to skip like that. Use a very, very low angle for your throw. It's actually a very big reflective angle, but okay, so keep moving here. Okay, so it says, turn the light off. A stone will skip only at wide angles from the normal. So we said a very narrow angle, but from the normal, now remember, normal is where it meets the surface, and it's 90 degrees. So about 70 degrees, you can get a nice, what you would call it, skipping stone. So that's basically what we're doing right now. We're skipping stones. But it's light. If that makes any sense. Okay. So there is a critical angle for these surfaces where the angle of incidence for which an angle of refraction equals 90 degrees when the light travels inside the one medium that borders air or a vacuum. So the idea is that you have it in something, and if you can have the angle of refraction equal 90 degrees, then it's not going to leave that medium. So if you know this critical angle to keep light inside this, let's say, prism, because that was a picture that we originally had, you can always just make sure you don't put it at the wrong angle, and it will go fine. Now, speed of light you really can't control. It's in there, so it's just a matter of the indexes of refraction. So here's what we're trying to determine. Now, since I want to determine the angle at which I can hit this barrier and keep it internal, so the light doesn't pass through, I need a very wide angle, but I have to find the critical angle. The angle of refraction has to be 90 degrees. Okay, so you're probably saying, well, what's this angle? What is the angle that we have to determine here that can keep this inside? Okay, moving right along. Okay, so deriving the critical angle equation. So this is what they do. Okay, I'm going to switch back down to my paper. Because I want to do this. It's more fun if I do it. I know. I've got problems. Okay, so N1 sine of theta equals N2 sine of theta. Now, this is already in our reference material. So we're looking for the critical angle. Okay, N1, N2. Now, they always say air or vacuum. So let's see. I'm just going to see how they do it. Do they make N1 the air or the vacuum? Okay, so they're saying this is the air. So the critical angle I want here is 90 degrees. It's going into air. So it's going from whatever this substance is into air. So the what you call index of refraction for air is just 1. Sine of 90. Okay, so let's do 1 sine of 90. So sine of 90, hope some of you know this already, but it's good to know like the extreme sines and cosines. Sine of 0, sine of 90, or, cosine of that, cosine of, 0. How about 0 to 90? I would think those. If I wanted to memorize a couple of trigonometric ratios, one of them would be sine of 90 and sine of 0, cosine of 90 and cosine of 0. From there, you can get everything. Everything's between 0 and 1. So, like, sine of 0 is 0. Sine of 90. If you have it in degrees, it makes no sense. Second quick. So sine of 90 is 1. Okay, I had that in radians, so clear it out again. So interesting things. Cos of 0 is 1. Cos of 90 is 0. Sine of 0 is 0. Sine of 90 is 1. As you get more involved in math, I hope lots of you guys are engineers and physicists in the future, because I want to be that inspiration to you. It's the most interesting subject ever. But sine of 90 is just 1, so it's just really 1 times 1. So what I have here is n1 sine of theta equals 1. Now this is going to be the critical angle. What angle can I project this light at to keep it internal? Well, here's what I'm going to do. I'm going to divide both sides by n1, the index of refraction of the material I'm using. So after I do that, I go sine of theta, which is the critical angle, is equal 1 over the index of refraction of the material I'm in. Now, knowing my sine and cosine functions and the inverse sine and cosine, which I do need the inverse, I'm going to do this. Sine of -1 of 1 over n1 equals theta. So I can find that critical angle all derived from this equation. I don't think they give this equation in the reference table. Double check. No. They give this equation in the reference table. They do not give this equation. But it's not that bad to derive. You just have to know that 90 degrees is the one that you want the refracted, I guess, though it's not really a refracted angle anymore, to be at. Okay, so it's going from the slower medium to the faster medium. Index of refraction and sine of that angle of reflection, I guess, refraction, is 90. Sine of 90 is 1. 1 times 1 is 1. So n sine of 1 theta of this critical angle equals 1. I divide both sides by that index of refraction for the material that we have, and I get this. Then I reverse it. Okay? So, going with that, since I derived that, I'm very proud of myself. I enjoyed that. They say here on the sheet, they keep it here, they don't do the... to me, I don't think it's as important to know. They usually don't give you that. I think they want you to usually figure that out. This is just, I guess, maybe keeping it simpler instead of doing a sine of -1. Why they did it. I just took it one step further. You're welcome. I'm so awesome. Okay, no, I'm not. But it was fun. Okay, so let's find the critical angle for lucite. So I'm shooting a laser light into lucite, and I want to find the critical angle that I can shoot it at, okay? And it'll keep it in. Okay, so here's what I'm looking at. Okay, let's go back to my piece of paper. Dum, dum, dum. Okay, piece of paper. Now, my piece of paper says this. Sine of -1, 1 over n1 equals the critical angle. So what's that critical angle? So the idea is I have a piece of lucite. And I have a laser in here. And I want to shoot it, but I don't want the laser to go outside. I want it to stay in and at least be 90 degrees, if not more. So I have to determine what this angle needs to be in order for this to stay in here. For this angle of refraction to be 90 degrees or greater. So what do I do? So I'm looking at him like, okay, here we go. So sine -1, 1. Well, n1 I know. I can find lucite in my indexes of refraction over here. Index of refraction for lucite, 1.5. Well, nice number. Not so big, not so small, equals theta. Okay, make sure you're on degrees, not radians. In my physics class, we don't use radians. Let's go. So clear. So second sine 1 divided by 1.5. Give me the measure in degrees. 41.81. I would round that to. You can go higher, right? I would say that's 42 degrees. So the critical angle for keeping the light within my, let's say, lucite prism has to be 42 degrees minimum. I could make it bigger than that, that's fine. But I don't want it any smaller than 42 degrees. Otherwise, then it's going to go out. Then it's going to shoot out. So I don't want it to shoot out. I want it to stay in. So I have to have this being a minimum of 42 degrees. And now if I make this bigger, and I shoot it over here, that's fine. That'll still keep it internal. And that might have some sort of reflection that's going like that or something like that. Oh, well, not like that. That. Remember, angle of incidence equals angle of reflection. Let's see if I can find one more problem in here before we call this an extra help session. Okay, so let's keep going. Lucite, boom. Look at this. Look at these guys. It's so predictable. We knew this already. 41.8. Look at that. 42. 41.8. So internal reflection. So you look at that. I don't know why they give that again. That's total internal reflection. These kinds of fibers are coated with materials that have low index of refraction, which is fast, and these are called claddings. That's what we do with fiber optics. Okay, so when the angle of theta 1, which we already said, I'm going to do my example there, is greater than the angle of, the name of this, the critical angle. So when our angle that we're shooting at is bigger than this critical angle. Well, actually, I think they could probably say equal to, or bigger than, greater than. Okay, so when bigger than. It's terrible math language. Theta 1 is bigger than the critical angle, total internal reflection. Now, the big trick here is the outside medium must be faster. Okay, so it's got to be usually shooting into air or a vacuum 99% of the time. Okay, so let's keep moving. Do I have anything else? Oh, see how good we are. Lucite. See, there you go. Greater than 41.8, and you're good. And it's not going to go through. It's going to have total internal reflection. Okay, when it equals 0.2, you get that. So I'm not quite sure if you define this as total internal reflection, but because it's not going out, but it's not going in. That's a tricky question. Okay. And then when theta, of course, is less than it, then what you have is you have these things passing through. Now you're going to say, well, wait, that theta, this is the wrong theta. You're talking about the theta from the normal. So 53 is greater, but you're measuring from the normal. So 53 minus 48 minus 90 is 47. Wait, is 37, excuse me, which is greater still. So I don't like how they labeled it. I would have labeled here, I would have put the normal. Okay. I'm assuming this is supposed to be lucite. This is supposed to be, it hits the lucite and goes back into the air. 53, yeah. Okay, so this, I would have labeled this angle, which in this case is 37. And then you get here, and angle 2, you could figure out just from the index of refraction of lucite, and then how it goes out. So you can figure out all these angles. Now, what is this angle here? Well, that's another tricky one. We really should be asking about this angle here. Can I do this problem? Do I want to do this problem? I don't think I want to do this problem. Okay, so internal reflection is this, is number 2. Okay, obviously the outside medium has to be fast. It has to be inside this medium. So the only place that's really even reflection here is 2. Yeah. That's the only one that actually even represents reflection. All these, well, 1, 4 does. But that's not internal reflection because the medium that it comes up against is water, and air is faster than water. You want the outside one to be faster. Okay, so keep going. Choice 2, of course, because we're so great. Refraction. Refraction could be 3, I'm thinking. Yeah, there you go. Man, I should take physics. What one is impossible? Number 1 is clearly impossible because you can't cross the normal. Light always crosses over the normal. I mean, you can't go back over the normal. What's wrong with this picture? Part of the ray would be refracted. Part of the ray would be reflected. Okay, so you actually should have drawn in, if you were doing this, another angle here. Just an idea. Let's look at this here. Now you can't say, oh, total reflection. It's not internal reflection because the outside medium is very fast on that. This was going from air into water. Air is fast, and then so you can't count the slower one. Give me a problem. I want a problem for this. Name the angle of incidence and the angle of refraction. Ooh, I like this question. Angle of incidence. So the light is traveling in this direction, if you see. So when it hits the medium, the borders here, you always measure it from the normal. So this angle, they do give us all 4 angles. This is the angle of incidence, because it's traveling this way, it's hitting here. The angle of refraction, again, is measured from the normal. So that's 41. Angle of incidence, angle of refraction. You always measure the angle between the normal and the light ray. This is meaningless. I mean, this could help you solve it if they didn't give you that and they gave you that. It's possible. But remember, your angles are these 2. The ones that border the normal. Okay. So next part we're talking about polychromatic light is turned, and it's a component's wavelength colors, turning it into it using a prism. You could separate them. Well, a polychromatic light means there's many colors, okay? So what you're doing is you're having a light of, let's say, a white light that's a base of all the colors of the rainbow, so to speak. So what happens is you put it through a prism, and you get an album cover, okay? This one is, if you guys know this Dark Side of the Moon by Pink Floyd, that picture on the front is a very, very famous album cover, and it's a light ray, polychromatic light, hitting a triangular prism, I guess a pyramid-shaped prism, and coming out the outside in its separate colors. Okay, this is very similar to why we have rainbows. The material that the light is traveling through is, in rainbows, sunlight is traveling through the water droplets. Here you're putting another type of light. I guess it's a laser light of some sort, but it's a combination of these colors. And what happens is it slows it down. Now, why does this work like this? That's a good question. Okay. So each color has a different wavelength. Okay? So as each color comes in here into this prism and it's reflected, what happens is the colors blend differently. Remember, the frequencies stay the same. So, well, all these lights are traveling together. They hit here. Now what happens is the frequency stays the same. So purple is going to be purple all along, right? But now purple is bent more than the other angles. Blue is bent a little bit less, yellow, red, orange, red. So each time they cross this medium, they bend a little bit more. Okay? So they cross here, they start bending. Now, because each is a different frequency, and we have, hold on, I'm going to go actually throw a formula up here real quick. Where's my light formulas? What was I thinking? I forgot what I was thinking. Very dangerous. Okay, so we got n1 sine of theta, n2 sine of theta, okay? So different angles coming in. To figure out that angle, I'm just trying to think how we would do that. How much is frequency? So what happens is they have the different wavelengths. Keep moving on, keep moving on. Let's see, maybe there's a better explanation. Good video here. Okay, so since red is the fastest, right? It's slowed the least and bent the least. And violet is the slowest, so it's slowed the most and bent the most. So as that polychromatic light enters the prism, purple is slowed, the velocity is slowed, and it's bent more. Okay. It's the slowest and it's bent the most. Now the fastest, red, wants to pass through it very, very, very quickly, and it bends hardly anything. So the slower, the more it's slowed down, the more it's bent, and the fastest, the more it goes straight through. So that's how it breaks up. Now, and also keep in mind that it's also going through two surfaces too. So it's meeting this boundary, and then it's meeting this boundary again. So it's traveling completely through. Alright, joke, ha ha ha. Okay, what we call this type of material that does this like a prism or a raindrop actually, is what we call a dispersive medium, a medium in which the velocity of waves depends on the frequency. So frequency will slow down certain waves. So frequency doesn't change. Glass, water. There's a rainbow. I know it's very hard to see in this picture, but there's a rainbow you see here. So what is happening here is, you always say, it's always after the rainbow happens. It's actually, at the moment of that rainbow, it's still raining there. You can, that's like the dividing line. That's where the water is coming down. Yours might be here in this safe spot, and you're dry, but the rain had just passed over you. So over here, as it's going, you're looking through that prism of light, okay, which is the raindrops, like the wall of water in a sense, and you get that prism effect. Again, total internal reflection. That you can see some of these videos. It says, cross out all the ray diagrams that are incorrect, justify your answers. So the question is, which ones here are right, which ones are wrong? Okay, so I'm going to look at this one. That could be right, because it's got a reflection and refraction. This is definitely wrong. 3 is not the right answer. Cross it out. Because it has to, right, light always has to cross the normal. Here, there's a reflection going on right here. between this one and this one. But you notice the angle of reflection and the angle of incidence, this is the angle of incidence, and the angle of reflection between the normal and the light wave reflected is obviously greater. They got to be equal. So in all these other examples, the reflected ray is equal. So this has an impossible reflection angle. This has an impossible refraction angle. And then we got these two. So the question is, which one is correct? So as you're looking at that, what do you got to remember here? It's going from air into water. From water into air. So what happens is, the more you bend an angle this way, the more this goes here. So this angle, I wouldn't expect when it hit the air for it to go straight up, or almost straight up as it is here. It gets bent much further from the normal as it goes into the faster medium. So 2 is our answer. So I hope this, I explained it to everyone. It's a half-hour video. Sorry if I took forever, but I know people were asking for this, so I'm glad I did it. I'll talk to you guys later. Have a great day. Everyone taking the AP exams, good luck.